Hi all, welcome back to discussion on quantum optics. So today we are going to discuss a special type of quantum state of light called coherent state. So till now we have discussed only one type of quantum state of light, that is basically called the number state or Fock state. It is the eigenstate of number operator or the Hamiltonian. Okay, or it is also called the energy eigenstate of light. Okay, now what is a coherent state? So coherent state is the eigenstate of annihilation operator A. Okay, so coherent state is the eigenstate of annihilation operator A. So we are going to denote this coherent state by symbol ket alpha. So therefore I can write the definition of the coherent state as the A acting on ket alpha become alpha times ket alpha. So here alpha is just a number, it can in general it can be a complex number, and we can also say that this alpha is the eigenvalue of this annihilation operator. So let this can be equation number 1. Okay, so alpha is eigenvalue and in general it can be a complex number. Okay, so what about the Hermitian conjugate of equation number 1? If you take the Hermitian conjugate of equation number 1, it become the bra alpha a dagger acting on bra alpha become alpha star bra alpha. Okay, now the next we are going to expand this ket alpha. It is the one possible state of light in terms of the number state, because the number state is the eigenstate of the number operator or the Hamiltonian. So obviously it would form a basis, because the complete set of the Hermitian operator act as a basis. So the ket n, the set ket n acting as a basis. So the ket n forms the complete set. Ket n forms a complete set. So therefore I can write the alpha equal to sum over n Cn ket n. Okay, now we already know that A acting on ket alpha is alpha into ket alpha. So if you substitute this equation, so let this can be equation number 3 and that is equation number 1. So substitute equation number 3 in 1, we'll get A acting on sum over n C n ket n become alpha into sum over n C n ket n. Now what is the action of A acting on ket n? So the Cn is just a number, complex number. So this can be Cn root n into ket n minus 1. And this can be simply written alpha sum over n Cn ket n. Now in order to equate the coefficient, so here summation is starting from n equal to 1, because n equal to 0 is not possible here, because inside the ket vector is starting from n minus 1. Okay, now the lowest possible the number state is ket 0. So therefore here the summation must start from 1. So I have changed, initially it is from 0 to infinity, but here it must be from n equal to 1. The reason is A acting on ket 0 is 0, it vanishes. So therefore n equal to 0 term would not be available in this particular equation. Okay, so that is why I have changed to n equal to 1. Now I can change my index from n equal to 1 to, instead of n, I can use m. Okay, so let's put n minus 1 as m. Okay, let's put n minus 1 as m. Okay, so then instead of n, I can write m plus 1. So it becomes sum over m equal to 0 to infinity. So C m plus 1, then root m plus 1, get m equal to alpha. Now here n is just a dummy index, so if I use either n or m, it doesn't make any difference. So whether it is sum over n equal to 0 to infinity Cn ket n, or if it is sum over m equal to 0 to infinity Cm ket m, both remain same. Okay, so if you look at this expression, so equation number 4, I can easily compare the coefficient of the different number states. Okay, so for each ket m, the terms means that the coefficients on both sides must be equal. Okay, because the different ket m, because the ket m and ket m plus 1 are completely independent, they are orthogonal to each other. Okay, Okay, that we already know, because remember the ket n is the eigenstate of a Hermitian operator. Okay, so therefore the different the eigenstate. Okay, so if you take the ket n and ket m, it would be orthogonal to each other. In general, I can write, if it is normalized, yeah, I can write the inner product nm would be delta mn. Okay, so that means the different eigenvalue, the eigenstate corresponding to the different eigenvalue or the different n values are orthogonal, they are independent. So therefore, in order to satisfy equation number 4, the each coefficient corresponding to the state ket m must equate separately. Okay, so consider for a particular state ket m. So for ket m here, on the left side the coefficients are cm plus 1 root m plus 1, that must be equal to alpha times cm. Okay, so that is what I have written here, cm plus 1 root m plus 1 equal to alpha times cm. Okay, now instead here it can also be written as cm root m become alpha times cm minus 1, or I can write cm equal to alpha by root m cm minus 1. So I will get now I am going to get the expression for coefficient. So cm is alpha by root m cm minus 1. Okay, so let this can be equation number 5. Okay, now I can substitute using equation number 5. I can find the expression for cm minus 1. So how will you write cm minus 1? So cm minus 1 will be alpha times root m minus 1 cm minus 2. Next, I can use equation number 5 to substitute cm minus 2. So similarly, if you repeat this procedure, I will get the expression for cm as a series. Okay, so it will be alpha by root m minus 1 up to alpha by root 1 c0. Okay, so the expression is equation number 5. You basically called the recursion relation, and from this recursion relation I will get the connection between the coefficient cm and the coefficient c0. Okay, so if you look at this, it has how many alphas? So there will be m alphas, so that will be alpha raised to m, and here we have root m into root m minus 1 up to root 1, and that is basically root m factorial. So finally I can write my coefficient cm as alpha raised to m by root m factorial times c0, or you can rewrite the cm into, as cn. So cn can be written as alpha raised to n by root n factorial times c0. So let this can be equation number 6. Okay, so now I can use equation number 6 into my equation number 3. So equation number 6 in equation number 3. So that would give the alpha equal to sum over n, alpha raised to n by root n factorial c0 ket n. So c0 is just a number, so there is no index involved here. I can take it outside, so it becomes c0 sum over n alpha raised to n by root n factorial ket n. Now what is c0? How we can find c0? Okay, we can find c0 using normalization condition. So I am imposing a condition that all this eigenstate of annihilation operator must be normalized. That is, the inner product of alpha with alpha must be 1. So if you use this condition, okay, so before that I can put, this can be equation number 7. So this ket alpha is c0 sum over n alpha raised to n by root n factorial ket n. Okay, so this is equation number 7, and this can be equation number 8. So substitute equation number 7 into 8. Okay, so first we have to find your bra alpha, then ket alpha. So let us keep the different indexes for the bra alpha and ket alpha. So for bra alpha I am going to denote, I am going to use m as for my index, and for ket alpha I am going to denote n as my indices. Okay, so in order to differentiate these two. Okay, so in both bra alpha and ket alpha, the c0 is common. Okay, in general c0 can be a complex number. So when you are taking bra alpha, it becomes c0 complex conjugate, so its product would be mod c0 square, and the remaining thing I have written here. Okay, now I can combine these two summation. So I can write this mod c0 square summation over mn alpha star raised to m, alpha raised to n by root of m factorial n factorial. Then you will have an inner product mn. Now what will be the inner product mn? So that we already shown that since the eigenstate of the number operator are orthogonal to each other, and if it is normalized, the inner product mn must be equal to canonical delta mn. That will be equal to 1 when m equal to n, and it is equal to 0 when m not equal to n. So that would be the inner product mn. So if you substitute it, so this equation become mod c0 square sum over mn alpha star raised to m, alpha raised to n by root of m factorial n factorial delta mn. Now we have to sum over it, sum over any one of the indices. Okay, suppose I am summing over m. Okay, so if I am summing over m, so first m will take value 0, then m will take value 1, m will take value 2. But this delta mn, this canonical delta mn will be always 0 except when m equal to n. So that means all the terms of this summation would be 0 except when m equal to n. So this summation would be non-zero only when m equal to n. So all other terms, so terms in the summation would be non-zero only when m equal to n. So for all other terms it would be 0. So for m equal to n terms, if you pick up the m equal to n term, it would be mod c0 square, then sum over n mod alpha square raised to n by n factor, that would be equal to 1. So this summation I can easily recognize is the exponential of mod alpha square. So that is mod c0 square e raised to mod alpha square equal to 1, or mod c0 is e raised to minus mod alpha square by 2. Okay, so let that would be equation number 9. Now if you substitute this equation number 9 into my equation number 7, equation number 9 in 7, so finally we'll get alpha as e raised to minus mod alpha square by 2 sum over n equal to 0 to infinity alpha raised to n by root n factorial get n. So that is basically the expansion of the coherent state in terms of number state. Okay, so next we have to discuss what are the characteristics, what is the importance of this coherent state. Okay, so we have already seen the Fock state, and we have already seen what are the characteristics of the Fock state. So the peculiar the characteristics of Fock states are: the first thing is it has a definite number of photons and it has a definite energy. So that means there is no uncertainty in the energy of the state. Okay, so if you look at the Fock state, the uncertainty in energy is 0, whereas it has a non-zero uncertainty for electric field. So if you look at the electric field, the uncertainty increases with the number of photons, and moreover if you look at the expectation value of electric field, and it is always 0. So these are the main characteristics of the Fock state. It is the energy eigenstate, it has a definite energies, and it has a definite number of photons. So there is no uncertainty in number of photons and as well as the energy, but it has the uncertainty in electric field, and the uncertainty in electric field increases with number of photons. So for Fock state, the uncertainty is minimum when photon number is 0. There is the vacuum state is having the minimum uncertainty, whereas it increases with the number of photons, and the expectation value of electric field is always 0. So therefore the quantum state, this Fock state is a purely quantum state. So usually what happens is when the number of photons increases, or when the quantum number increases, the quantum state become, or the quantum system will behave classically. So and that is basically what is called the Bohr's correspondence principle. Okay, so but the Fock state doesn't show that behavior. So even though if you increase the the quantum number n, the photon number n, there will not be any variation in the expectation value of electric field. The expectation value of electric field is always 0. But if you look at a classical light, the classical electromagnetic wave, the simple solution of electric field is the harmonic oscillations. Okay, the harmonic wave or sinusoidal wave. So that is the waveform classically. But your Fock state is not having the harmonic nature even at a very high quantum number. Okay, so the electric field, the expression value of electric field is 0 even at high, even at large number of photons. Okay, that would be better term. Even at large number of photons. Okay, so therefore this Fock state is a pure quantum state. So there is no classical analog for Fock state. Okay, so next we can discuss what is the behavior of our coherent state. Okay, so for that we are starting with the expression for the electric field operator. So if you including the time dependence using the Heisenberg picture, the electric field I can write as I square root of h cross omega by 2 epsilon 0 v a e raised to I k dot r minus omega t a dagger e raised to minus I k dot r minus omega t. So this is the expression we already used earlier. Okay, so the time dependence also given here, and this time dependence you can derive using the Heisenberg picture. It is basically the IH cross dA by dt would be commutator AH. So using this we can find the time dependence of your annihilation operator and as well as the creation operators. Okay, now our task is to find the expectation value of electric field in the coherent state. So the expectation value of electric field in the coherent state, okay, I will denote by this symbol. Okay, and this ket alpha in the subscript denotes it is in the coherent state. Okay, because we already discussed the expectation value of electric field for the number state. So in order to distinguish these two, I have just introduced a subscript. Okay, so this can be known as the inner product alpha ex alpha. Okay, so just substitute your ex. Okay, so let this can be equation number 10 and this can be equation number 11. So use equation number 11 here. Okay, so just substitute it. Now you will get the inner product of alpha a alpha and alpha a dagger alpha. So alpha a alpha would give simply the number alpha, complex number alpha, and alpha a dagger alpha would give would leave alpha star outside. Okay, so this would be your the expectation value of electric field. I have simply skipped one step here because we have to calculate alpha a alpha and alpha a dagger alpha. So using the definition of the coherent state, you can simply find this as alpha into alpha alpha, and this alpha is just a number, it can be taken outside. Okay, so this would be alpha into alpha alpha, and this is 1. Okay, since the ket alpha are taken to be normalized. Okay, so only this would be equal to alpha, and that is what is written here. Okay, so the first term would become alpha. The first inner product of alpha a alpha would be alpha, and the inner product alpha a dagger alpha would be alpha complex conjugate. Okay, so therefore the expectation value of electric field in the coherent state would be I square root of h cross omega by 2 epsilon 0 v. Now since alpha is a complex number, I am going to denote my alpha as mod alpha times e raised to I theta. So alpha is mod alpha e raised to I theta, that is given here, and alpha star would be mod alpha e raised to minus I theta. So mod alpha can be taken commonly outside. So this become e raised to I k dot r minus omega t plus theta. Then e raised to minus I k dot r minus omega t plus theta. Okay, so this is just e raised to ix minus e raised to minus ix, and that is same as 2I sin x. Okay, so if you use that result, I can write the quantity inside the bracket as simply 2I sin of k dot r minus omega t plus theta, and I into I will become minus, and that minus can be taken inside this the phase. So therefore, finally, I can write the expectation value of electric field as 2 into mod alpha square root of h cross omega by 2 epsilon 0 v sine of omega t minus k dot r minus theta. Now, surprisingly, if you look at this expression is equivalent to the classical electric field, the electric field of a classical electromagnetic wave. It has a harmonic solution, or it has the harmonic form. Okay, so therefore I can say that the expectation value of electric field in coherent state looks like the classical field. So if you want to get the uh, uh, the the classical counterpart of the quantum light, then it must be the coherent state and not the Fock state. The Fock state is never the classical counterpart, but whereas the coherent state can behave classically at higher quantum numbers. So I want to emphasize this fact. The Fock state we already discussed, although it is very simple state, but that is a purely quantum mechanical state of light. There is no classical counterpart for it. Whereas a coherent state has a classical counterpart, and for at a high quantum number, the coherent state may behave classically. Okay, so that's about the expectation value of electric field. Now we can calculate what would be the uncertainty in the electric field delta E. So for that we have to calculate the square of the expectation value of the square of the electric field. So just calculate Ex square first. Okay, so before that let us number these things. So electric field operator, I have written equation number 11, and find the expectation value of electric field can be written as equation number 12. Okay, so I can write the coherent state I have at high alpha, whereas the Fock state is a pure quantum state with no classical counterpart. Okay, so coherent state I can return by symbol ket alpha, and the Fock state I can return by symbol ket n. Okay, so this ket alpha can behave classically at high quantum numbers. Okay, so next we can calculate Ex square. So this Ex square, all the steps I have shown here how to calculate Ex square. Okay, so that you can do it yourself. Okay, I maybe skipped a few steps here, but I am very sure that this you can do yourself. This can be equation number 13. And next we can calculate the expectation value of the square of the electric field, and that step also I am leaving to you. You can do it yourself. Okay, so just pause this video and do all the calculations. Okay, so all the steps are shown here. Okay, and finally once you get, I will be using the same expression. The alpha can be divided into its real part and complex part. And finally you can just pause this video and just check your calculations. Just ensure you are getting the same thing. Okay, so these are the steps. I am not going to explain each steps in detail. Okay, all these are a simple algebra. I think you can do it yourself. So finally, the expectation value of the electric field will get h cross omega by 2 epsilon 0 v times 1 plus 4 mod alpha square sine square omega t minus k dot r plus theta, and this can be my next equation. It can be equation number 14. Okay, so if you are not getting the result, just pause this video and just copy it. Okay, so that is equation number 14. And finally I can calculate the uncertainty in electric field for the coherent state. And if you calculate the uncertainty electric field, that would be simply equal to square root of h cross omega by 2 epsilon 0 v, and which is same as the expectation value, the uncertainty of electric field in vacuum state. So this is equal to the uncertainty of electric field in vacuum state. That is, the uncertainty in electric field operator in coherent state is same as the vacuum fluctuations of electric field. And the expectation value of electric field in coherent state has harmonic dependence as like classical fields, whereas the expectation value of electric field in Fock state is always zero. So hence the coherent state is treated as a nearly a classical like state, and Fock state is purely a quantum state. So that is a summary of this session. Okay, so finally we can find out what about the expectation value of the photon number, and as well as its uncertainty. Okay, so the expectation value of photon number, the ket n, is alpha dagger a ket alpha, and that will be simply equal to mod alpha square. And if you look at the uncertainty, okay, you have to find the expectation value of the square of the number operator. Okay, so remember this n I can put better ket n hat is a number operator which is a dagger a. Okay, so the expectation value of square of number operator, that would be mod alpha square alpha raised to 4. Okay, so let give the different equation numbers. So let this is equation number 15, and this is equation number 16, equation number 17. So if you just take the difference between 17 and square of equation number 16 and find its square root, you will get the uncertainty, and let that be equation number 18. So in getting the uncertainty in photon number is equal to the square root of the expectation value of the number of photon. Now this is a kind of a distribution. So this kind of distribution usually called the Poisson distribution. Okay, so if you want to clearly get the Poisson distribution, we have to find the probability to find the number of photons, number of n photons in the coherent state. So the probability to find n photons in the coherent state, that is simply the inner product between n and alpha, the mod square of n alpha, in the inner product n alpha. So if you take the mod square of this inner product between the number of the Fock state with photon n and alpha, so that will you give e raised to. Okay, so that is very simple to do. Just substitute ket alpha, just expand ket alpha in the number state. So since we already used n here, just use the index as m. So sum over m equal to 0 to infinity e raised to minus mod alpha square by 2 by root m factorial alpha raised to m get m. Okay, so just take the inner product. So this inner product would be nm, and that is a canonical delta mn. And in this summation, only one term of the summation will be non-zero, only for m equal to n. So that would give this equation would give mod square of e raised to minus mod alpha square by 2 by root n factorial alpha raised to n, or it is simply e raised to minus mod alpha square raised to n into by n factorial. Remember, this mod alpha square is nothing but the expectation value of the photon number, so our average photon number. So the probability to find n photons in the coherent state ket alpha would be e raised to minus the expectation value of n raised to n divided by n factorial. So this kind of distribution is called the Poisson distribution. And if you plot the graph between the probability to find the number of photon and the number of photon, so this n is the number of photon, it can start from 0 to 40 up to 10. Okay, so if you have a coherent state ket alpha, so remember the ket alpha, it is basically a superposition of many states. Okay, so let us expand it. So this ket alpha is e raised to minus mod alpha square by 2. Then the first term is alpha raised to n, that would be 1 or ket 0 plus alpha into ket 0 plus alpha square by square root of 2 alpha raised to 1 divided by 1 get 1 plus alpha square by root 2 get 2 plus etc. Okay, so this is basically your coherent state. So it is the series of different Fock state, the get 0 state, get 1 state, get 2 state, etc. The get 0 state contains 0 photons, and this is corresponding to 1 photon, this state corresponding to 2 photon, etc. Now what's the probability to find 0 photon? That would be, okay, suppose this get alpha is C0 0 plus C1 1 plus C2 2 plus etc. The probability to find 0 photon is mod C0 square, and the probability to find 1 photon is mod C1 square. The probability to find 2 photon is mod C2 square, and I have to find it. The probability to find n photon is the inner product n get alpha mod C0 square. That is what we have done. Okay, so here on the left side we have plotted the probability to find n photons in a coherent state get alpha, and the photon number, this photon probability distribution like this for the expectation value of the number of photon is equal to 2. If you increase, if the number of photon, what is the expectation value of number of photon, that is equal to mod alpha square. For mod alpha square is equal to 2. Suppose if mod alpha square is equal to 6, then this peak would be corresponding to 6. Okay, so there will be the variation in the graph. Okay, so this graph may like this. Okay, so this kind of distribution you can see in the probability of number of photon for coherent state. But whereas for the Fock state, for get 1 state, there is a probability, the 100% probability to find the number of n photons. Okay, so suppose get 1 means the probability to find 1 photon is 100%, and the probability to find 2 photon is 0. But for get 2, the probability to find 2 photon is 1, and probability to find 1 photon is 0. Here probability to find 1 photon is 1, and probability to find 2 photon is 0, and etc. Whereas for coherent state, the coherent state is superposition of light, quantum states of light, the Fock states of light with a different photon number. So there will be a definite probability, the definite non-zero probability for different photon numbers, and that probability distribution is obeying the Poisson distribution. So that's all about the coherent state. So if you summarize the coherent state, okay, so the coherent state is the eigenstate of annihilation operator, okay, that is A acting on ket alpha become alpha into ket alpha, and its electric field, the expectation value of electric field, if you look at the expectation value of electric field is has a mathematical structure corresponding to the classical field, and the uncertainty in the electric field is equal to the vacuum fluctuation. So that is a very important factor. For a coherent state, the uncertainty electric field is independent on number of photons. So whatever be the average number of photon. So for coherent state, the expectation value of number of photon is mod alpha square. So if you increase alpha, the vacuum fluctuation remains same. What is the vacuum fluctuation? Which is square root of h cross omega by 2 epsilon 0 v. So it is independent on the average number of photon. Okay. And what was the uncertainty in the number of photon? The uncertain number of photon is same as mod alpha, and therefore the probability to find the n photon in photons in coherent state, delta alpha follows Poisson distribution. So this is the all the characteristics of the coherent state. It is the eigenstate of annihilation operator with non-zero expectation value for the electric field, and moreover the expectation value of electric field has a classical representation. Okay, so it may behave a classical light at higher quantum numbers. That is when the number of photon increases. And if you look at the uncertainty in the electric field, it has a minimum uncertainty. Its uncertainty equal to the uncertainty of vacuum, or it is equal to the vacuum fluctuation uncertainty. And the expectation value of number of photon is mod alpha square, and the uncertain number of photon is equal to mod alpha, and the probability distribution of number of photon obeys the Poisson distribution. Okay, so with this we have discussed two different types of the quantum states of light, which is very much useful in the further discussion of quantum optics. One is a pure quantum state called Fock state, and other one is a state which can have a classical counterpart called the coherent state. Okay, so thank you very much for watching this video. In the next class we'll start the discussion of the Jaynes-Cummings model, which is the fundamental model of the starting point of quantum optics. Okay, thank you.